So we've already seen how to compute the number of subsets that have a specific element of a set. Well, what if this time we ask ourselves, how many subsets have not just one specific element, but also another? In this case, how many subsets of A have 2 and 3? Now, it's very important to notice that we've underlined and, because when we say 2 and 3, we are counting the subsets that have to have both of them, not just one of them. So for this smaller set, what we're going to do is quickly write out all the subsets and quickly see what the answer should be. Okay, every single subset of A is here. We know that there's going to be 8 of them based off of what we computed when we first started doing this sort of topic. And what do we see? How many of these subsets have exactly 2 and 3? Don't just have 3 and don't just have 2. So let's have a look. Well, the empty set doesn't have 2 or 3. The set with just 1 doesn't have 2 and 3. The set 2 has 2, but it doesn't have 3, so we don't count it. We want it to have both of them. Similarly for the set with just 3. Okay, the set 1 and 2 has 2. Still, we're missing the 3. The set 1 and 3 is missing the 2. Oh, there we go. We've seen the first set that has both 2 and 3 is the set containing just 2 and 3. Okay, fantastic. And the very last set that contains both 2 and 3 is going to be the set containing all of the set of A. Fantastic. But, of course, this is a method that you should never ever use in your counting problems, because when you get counting problems that are going to have 4, 5, and anywhere greater than 5 elements, you're simply not going to have enough time, or it's just not going to be a good use of your time writing out every single subset and then going through and finding how many of them meet your criteria. So how would you have found that the answer here is in fact going to be 2 without writing out all of these subsets and counting them? Well, we're going to use the notation we've already established, the notation of 2 to the power of n and our n choose k notation. We're going to solve this problem using both methods. So for the 2 to the power of n method, we know that 2 to the power of n is something we often use to compute the total number of subsets. The n here is usually going to be the number of elements in the set you're wanting to compute. So originally we would have said this is 2 to the power of 3, and that's 8, and that's how many total subsets there are. But another way of thinking about this power n here is that n at the end of the day is really just going to be how many elements are not fixed in your problem. So in this problem, we need to have it so the subsets have 2 and 3. So the 2 and 3 are fixed because there is no question whether or not they're going to be in our subsets. They will be in our subsets. So the only free variable, or the only non-fixed variable we have, element, is going to be 1. We only have one element in this entire set that is not going to be fixed, so our n instead is going to be a 1. And 2 to the power of 1 is in fact going to be 2, and that is exactly the answer we got when we wrote out all of our subsets. The second way you could have done this, and I think this way is much better because it shows you your thinking process of how you would count these subsets, is using the n choose k method. Now this method is a little bit longer, but it also makes a little bit more of intuitive sense. So we know that if you want to compute the total number of subsets using this technique, what you would say is, okay, well, n is still going to be the number of non-fixed variables we have, right? So if you want to compute the total we had originally was 3. So you would say you have 3 choices, and the first thing you can do, the first set of subsets you can have is you can have how many of these 3 can you choose none of? Then you can say, okay, well, if I have 3 choices, how many ways can I just choose one of the 3? Then you can say, okay, out of these choices, how many ways can I choose a pair of 2? And finally, you can say, well, out of these 3 choices, how many ways can I choose all of them? In this case, all 3. And we found that this answer was, in fact, 8, because this is 1, this is 1, this was 3 factorial over 1, 2. So this was also 3, and then this is 3. So we found that's what each one of these n choose k was, and that's, of course, equal to 8. Okay, But now that we are fixing our elements 2 and 3, we have no say of whether or not those are our choices, right? They have to be in our subsets. You can think of it like in the example I gave with the teacher, where if you are a teacher in a classroom like this, so let's say you are a teacher in a classroom, and originally you need to choose 2 students to go do something, right? You have 9 students to choose from here, so your answer would have been there's 9 choices, and you need to choose. How many ways out of your 9 students can you choose 2 of them? This would have been your original answer. But let's say we are fixing one of the students, right? Just one. We're gonna forget about fixing 2. Let's say you have to have this student go do whatever you're gonna have to go do. And then you have to choose a second student because you need 2 students in total, but you're definitely going to have this student be one of the 2. Well, what we then find is it's no longer going to be 9 choose 2, it's in fact going to become 8 choose 1. Why is it 8 choose 1? Well, 8 because you no longer have 9 options, you're only choosing between 8 students. And 1 because you're no longer choosing 2, you're choosing only 1 student. This is going to be a very similar form of logic here. So originally, this is how we looked at the total problem. But because we are fixing our 2 and 3, we no longer have 3 variables. This top line down here, we no longer have, oh, this is a bad marker. We no longer have the ability to choose from 3 elements in our set. We now instead have to choose from 1, right? You can only choose 1. You can think of it like saying, let's set aside, let's create a set and set aside 3 and 2. And what we're going to say is, okay, this set can be the following. The sets we're looking at can be the following. They can be that out of the 1 choice we have left, it's 1 choose nothing. We can just choose nothing, and our set will just be 2 and 3. Then we can say, well, we can take the 1 choice we have, and how many ways can we choose that 1 option? Or this case is saying, well, to our fixed sets that have to have 2 and 3, we can add nothing, leaving it as it is. Or how many ways can we add 1 thing? So in this case, you'll add an extra comma, and there will be something here. Or in this case, this something is going to be 1. And what do we find? Since these are the only 2 options left, you cannot say something like 1 choose 2, because if you have 1 option, how could you choose it twice? It doesn't make any sense. So our answer is going to be computing these 2 options here. And what is that going to be? Well, 1 choose 0, there's only 1 way to choose nothing. So that's going to be 1. 1 choose 1 is also just going to be 1. There's only 1 way to choose something when you only have 1 option. So the answer to this is going to be 1 plus 1, which is equal to 2, which is exactly the answer we got in our other 2 methods. So this is how you would compute how many subsets have a specific element in them, but it's 2 of them, and it must, in this case, have both of them.